Semiconductor Wafer Fabrication Process. Semiconductor wafer fabrication is the foundation of modern electronics, enabling the production of microchips found in smartphones, computers, vehicles, and countless other devices. This process is highly complex, involving hundreds of precise steps carried out in cleanroom environments. From raw silicon to finished wafer, every step must be tightly controlled. Achieving nanoscale precision is essential, as features on a chip can be thousands of times smaller than a human hair. At these scales, even microscopic contamination or slight variation in temperature can affect device performance. Advanced manufacturing techniques, such as photolithography, chemical vapor deposition, and atomic layer etching, are required to build these intricate structures layer by layer. This presentation offers a clear and accessible overview of the process for general audiences, highlighting its challenges, sophistication, and importance in powering the technologies we rely on daily. Definition and core process steps. Wafer fabrication is the intricate, multi-step manufacturing process that transforms pure silicon into the microchips that power today's digital devices. It involves building complex electronic circuits on thin slices of silicon, called wafers. The process takes place at the atomic level, requiring incredibly precise control. Fabrication involves three essential categories of steps: deposition, patterning, and modification. Deposition refers to the addition of material layers onto the wafer's surface. These layers can be conductive, insulating, or semiconducting. Patterning is the process of creating intricate circuit designs by selectively removing or modifying parts of these layers, typically using photolithography. Finally, modification involves changing the physical or electrical properties of selected regions, such as through doping, oxidation, or annealing, to fine-tune how the chip performs. Together, these core steps are repeated many times to build up the multi-layered architecture of an integrated circuit. Scale and impact of wafer fabrication. Wafer fabrication is not only incredibly complex, but also occurs at an enormous global scale. Each year, over 1.15 trillion chips are shipped worldwide. These chips are the foundational components behind virtually every digital device. Despite their tiny size, each chip requires more than 3 months of manufacturing time. This lengthy process involves thousands of tightly coordinated steps, from initial silicon wafer preparation to final inspection and packaging. Precision is critical, as features on modern chips are measured in nanometers, 1/1,000,000th of a meter. At such minuscule scales, even the slightest variation can impact performance or cause defects. The resulting chips power everything from smartphones and computers to vehicles, smart homes, and critical medical devices. The semiconductor industry's impact is universal, driving innovation across countless sectors. Understanding this fabrication process reveals why it's considered the backbone of the digital age, from pure silicon crystal to precision-cut wafers. The journey from raw silicon to a processed wafer begins with crystal growth. Using the Czochralski process, silicon is melted at around 1450 degrees Celsius, and a single seed crystal is dipped into the molten silicon to slowly pull out a large cylindrical crystal called an ingot. This crystal is highly pure, typically 99.99%, and has a uniform atomic structure. Ingot formation produces a monocrystalline rod, often with a diameter of 300 millimeters. Next, the ingot is carefully sliced into thin discs using a diamond saw, with each wafer measuring approximately 0.775 millimeters thick. Precision is essential to maintain uniformity across all wafers. After slicing, each wafer undergoes a meticulous polishing step. This creates a mirror-like surface with less than 0.1 nanometers of surface roughness. The entire polishing process takes place in ultra-clean environments to avoid contamination. The result is a stack of wafers, ready for semiconductor processing. Wafer specifications and production output. Each silicon wafer used in semiconductor manufacturing is produced to strict specifications. The industry standard diameter is 300 millimeters, offering a large surface area for building many chips on a single wafer. Thickness is controlled to about 775 micrometers with a tight plus or minus 15 micrometer tolerance to ensure uniformity during processing. Purity is critical. Each wafer must consist of ultra-pure silicon with 99.99% purity to maintain electrical performance. Surface roughness must be less than 0.1 nanometers, achieving a mirror-like finish essential for lithography. Production output is continuous, operating 24/7, and from a single silicon ingot, approximately 200 wafers can be sliced. Rigorous quality control measures are implemented throughout, including verification of crystal orientation, limits on surface defects below 0.1 particles per square centimeter, resistivity uniformity within plus or minus 5%, and processing within a Class 1 cleanroom. These controls ensure consistency and reliability at every stage of semiconductor fabrication. Building layers and creating insulation on silicon wafers. In semiconductor manufacturing, two key techniques, thin film deposition and thermal oxidation, are used to build layers and create insulation on silicon wafers. Thin film deposition includes several processes. Chemical vapor deposition, or CVD, operates at 400 to 1000 degrees Celsius and involves gas phase reactions to form solid films. Physical vapor deposition, or PVD, runs at room temperature to 500 degrees Celsius and uses physical processes like sputtering or evaporation. Atomic layer deposition, or ALD, provides angstrom-level precision by depositing one atomic layer at a time. Spin coating uses liquid-based deposition to form films that range from nanometers to micrometers thick. On the other side, thermal oxidation is a high-temperature process used to grow silicon dioxide on wafers, typically at around 1100 degrees Celsius. It runs between 900 and 1200 degrees Celsius in a furnace, using oxygen or steam atmospheres. Growth rates vary from 10 to 100 nanometers per hour, with a uniformity of plus or minus 2% across the wafer. Common materials, oxidation types, and process sequence. In semiconductor fabrication, a variety of materials are used to build the layers of a device. Common materials include metals like aluminum, Al, copper, Cu, tungsten, W, and titanium, Ti, which are used for electrical conductivity. Dielectrics, such as silicon dioxide, SiO2, and silicon nitride, Si3N4, serve as insulating layers. Semiconductors like polycrystalline silicon, poly-Si, and gallium arsenide, GaAs, are used for active electronic behavior. Oxidation types play a key role in insulating layer formation. Dry oxidation, which uses a pure oxygen atmosphere, produces high-quality, dense oxide layers, though it grows slowly. Wet oxidation uses water vapor, H2O, and enables faster oxide growth, which is ideal for thicker layers where speed is a priority. The typical process sequence starts with a clean wafer, followed by thermal oxidation. After that, layer deposition occurs. The final step is a quality check to ensure that specifications and performance standards are met. Precision pattern transfer, using UV light technology. Lithography is a critical step in semiconductor fabrication used to define precise patterns on silicon wafers. This process utilizes ultraviolet, UV light, to transfer patterns through a mask or reticle onto a photoresist-coated wafer. There are three main types of UV lithography based on wavelength. EUV, or extreme ultraviolet lithography, uses a 13.5 nanometer wavelength and supports advanced nodes like 7 nanometers. DUV, or deep ultraviolet, operates at 193 nanometers, typically used for 22 nanometer nodes. I-line lithography uses a 365 nanometer wavelength and is suitable for features larger than 180 nanometers. The four-step lithography process begins with photoresist coating, applying a light-sensitive layer ranging from 100 to 500 nanometers thick. Next, UV exposure occurs for just milliseconds, transferring the pattern. Then, a chemical development step, lasting 30 to 90 seconds, reveals the pattern. Finally, inspection ensures pattern accuracy with 100% quality checks before continuing the fabrication process. Critical parameters and technology in lithography. Several critical parameters define lithography performance in semiconductor manufacturing. Resolution refers to the minimum feature size that can be printed, typically ranging from 7 to 22 nanometers. Overlay accuracy, which ensures that each new layer aligns precisely with the previous one, must stay within plus or minus 1.5 nanometers. CD control, or critical dimension control, ensures consistent line widths and patterns, with a precision of plus or minus 1 nanometer. Throughput, measured in wafers per hour, WPH, shows the tool's productivity, typically around 200 WPH. Technology nodes indicate feature size progression, with smaller nodes like 7 nanometers or 14 nanometers representing more advanced, compact designs. Photoresists are categorized into two types: positive resist, where exposed regions dissolve and offer high resolution, and negative resist, where unexposed areas dissolve, yielding high contrast. Industry leaders in lithography equipment include ASML for EUV systems and Nikon and Canon for DUV systems, all playing vital roles in advancing semiconductor technology. Precision material removal for pattern definition. Etching is a key step in semiconductor fabrication used to remove specific materials with high precision. Plasma etching, also known as dry etching, uses RF plasma to generate reactive species that etch the wafer. It operates with a 13.56 MHz RF frequency, in a pressure range of 0.1 to 10 millitorr. The power applied ranges from 100 to 500 watts, while temperatures are controlled between 0 to 100 degrees Celsius. Plasma etching offers excellent selectivity, up to 100.1, meaning it can etch one material much faster than another. This enables fine patterning with vertical sidewalls, called anisotropic etching. Wet etching uses liquid chemicals in a bath. Hydrofluoric acid, HF, is used for etching silicon dioxide, potassium hydroxide, KOH, for anisotropic etching of silicon, and phosphoric acid, H3PO4, for selectively etching silicon nitride. Wet etching typically results in isotropic profiles, with curved or undercut sidewalls, while plasma etching supports anisotropic vertical profiles. Method comparison and etch process overview. There are three primary etching methods used in semiconductor manufacturing: RIE, wet etch, and ICP. Reactive ion etching, or RIE, offers a fast etch rate with excellent process control and produces anisotropic profiles, meaning vertical sidewalls are maintained. Wet etching, on the other hand, delivers medium speed with good control, but the etch profile is isotropic, resulting in undercutting beneath the mask. Inductively coupled plasma, or ICP, provides very fast etching, excellent control, and vertical profiles, making it ideal for deep and narrow features. Several critical parameters define process performance. Etch rates range from 50 to 500 nanometers per minute. Uniformity across wafers is typically within plus or minus 3%. High aspect ratios like 50.1 can be achieved, and selectivity between materials may reach up to 100.1. Common plasma gases include CF4 and CHF3 for SiO2 etching, Cl2 and BCl3 for silicon and polysilicon, and argon or oxygen for physical etching. Leading equipment providers include Lam Research, Applied Materials, Oxford Instruments, and Siemens. Ion implantation process. Ion implantation is a key technique used to modify the electrical properties of semiconductor wafers by introducing precise amounts of dopants. The process begins with an ion source that generates dopant ions. These ions are accelerated into a focused ion beam and directed toward a wafer target. Common dopants include boron for p-type doping and phosphorus or arsenic for n-type doping. Boron acts as an acceptor, while phosphorus serves as a donor. Arsenic, being heavier, is typically used when a higher dose is required for deeper or more concentrated implantation. Critical parameters in this process include energy, dose, and depth. The energy of the ions, ranging from 1 to 200 keV, determines how deeply the ions penetrate the substrate. Dose, measured in atoms per square centimeter, typically ranges from 10 to the power of 12 to 10 to the power of 16 atoms, cm2. Depth control, vital for junction formation, is tunable between 10 and 500 nanometers. Annealing and conductivity control. Annealing is a critical thermal process applied after ion implantation to restore and optimize the electrical and structural properties of the semiconductor material. Typically performed at high temperatures, ranging from 800 to 1100 degrees Celsius, annealing serves three essential purposes. First, it repairs implantation-induced crystal damage, restoring the silicon lattice structure through thermal healing. Second, it activates dopants by moving them into substitutional sites within the crystal lattice, enabling them to contribute to electrical conductivity. Third, it helps control dopant diffusion, optimizing the depth and sharpness of dopant profiles for precise device performance. This process directly affects the material's electrical conductivity. As dopants become electrically active, resistivity changes dramatically. Effective annealing allows engineers to fine-tune resistivity across a wide range, from highly conductive at 10 to the power of 3 ohm centimeters to very resistive at 10 to the power of 3 ohm centimeters, providing critical control over semiconductor functionality and device behavior. Semiconductor types and process conditions. Semiconductors are classified based on their doping characteristics. P-type semiconductors are formed by adding acceptor dopants, which introduce holes or positive charge carriers. Common P-type dopants include boron, B, aluminum, Al, gallium, Ga, and indium, In. In contrast, N-type semiconductors are created using donor dopants that contribute free electrons as negative charge carriers. Typical N-type dopants include phosphorus, P, arsenic, As, and antimony, Sb. Intrinsic semiconductors, such as pure silicon, contain no dopants and exhibit high resistivity, making them less conductive until intentionally modified. Key process conditions ensure accurate and uniform semiconductor processing. Annealing typically occurs at 1000 degrees Cc, with process times ranging from 15 to 60 minutes. These steps are performed under vacuum conditions, often at pressures near 10 to 6 torr, and require tight temperature uniformity, typically within +2 degrees C, to ensure consistency across the wafer. Leading equipment providers include Applied Materials for implant systems, Axcelis Technologies for ion implantation, and ASM International for annealing furnace solutions. Sputtering deposition and metal materials. Sputtering deposition is a physical vapor deposition, PVD, method used to create conductive layers for electrical connections and multi-layer wiring in semiconductor devices. In this process, energetic ions strike a metal target, ejecting atoms that then condense on the substrate to form a thin film. Sputtering enables precise control over film thickness and composition. Alongside PVD, other deposition techniques include chemical vapor deposition, CVD, which uses gas phase reactions, atomic layer deposition, ALD, known for its atomic level thickness control, and electrochemical deposition, ECD, often used for copper plating in interconnects. Selecting the right metal is critical for minimizing electrical resistance. Copper, Cu, is preferred for its low resistivity of 1.7 micro-ohm centimeters, making it ideal for high-performance interconnects. Aluminum, Al, with a resistivity of 2.8 UR/cm, is still used in some applications. Tungsten, W, though higher in resistivity at 5.6 UR/cm, is valued for its durability and compatibility with high-temperature processes. Electrical connections and multi-layer wiring. To build advanced semiconductor devices, it's critical to form electrical connections and multi-layer wiring. One of the key techniques for depositing metals is sputtering deposition, a type of physical vapor deposition, or PVD. In this process, a target material is bombarded by ions, ejecting atoms that then deposit onto the substrate. This method is widely used for creating metal interconnects. In addition to PVD, there are other deposition techniques such as chemical vapor deposition, CVD, which uses gas phase reactions, atomic layer deposition, ALD, known for its precision at the atomic scale, and electrochemical deposition, ECD, which involves metal plating using electric current. When selecting metal materials, electrical resistivity plays a major role. Copper, Cu, with a resistivity of 1.7 micro-ohm centimeters, is preferred for low-resistance paths. Aluminum, Al, has 2.8, and tungsten, W, is higher at 5.6. Each metal is chosen based on process compatibility and performance needs. Multi-layer stack and conductivity. Modern semiconductor chips rely heavily on multi-layer metal stacks to form complex interconnections. These stacks often include more than 10 layers, each serving a specific routing purpose to connect millions or billions of transistors. Vertical connections between these metal layers are made through vias, tiny cylindrical holes that allow electrical signals to pass between levels. As chip dimensions shrink, so do the vias. In advanced chips, via diameters typically range from 10 to 50 nanometers, requiring high precision in patterning and deposition techniques. One of the critical performance goals in these interconnects is maintaining high conductivity. Low electrical resistance is essential for reducing power loss and ensuring fast signal transmission. As more layers are added, material selection and process control become even more crucial to preserve signal integrity and minimize delay throughout the integrated circuit. CMP planarization and damascene process. Chemical mechanical planarization, or CMP, is essential for achieving a flat, even wafer surface before moving to the next layer in chip fabrication. It uses a combination of physical abrasion and chemical slurry, typically silica-based, SiO2, to polish surfaces. CMP operates with a uniformity of +5 nanometers and a removal rate that ranges from 50 to 200 nanometers per minute. The applied pressure typically falls between 3 to 7 psi. Uniform planar surfaces are necessary to support subsequent lithography and metallization steps. CMP is the final step in the damascene process, which begins with trench etching to define metal lines. This is followed by deposition of barrier and seed layers, often using Te, Te-N, and copper. Next comes copper fill through electroplating. CMP then removes excess material to leave a flush, embedded structure. Key parameters such as line width, aspect ratio, RC delay, and current density guide process optimization. Leading tool suppliers include Applied Materials, Lam Research, Ibera Technologies, and Novellus Systems. Final steps and complete semiconductor journey. The final phase of semiconductor manufacturing involves wafer testing, IC packaging, and comprehensive process flow completion. Wafer testing includes 3 major checks: parametric testing to confirm electrical characteristics, functional testing to ensure correct circuit behavior, and speed sort to classify chips by performance. Devices that pass all tests move on to IC packaging. Packaging formats vary by application and include BGA, ball grid array, QFN, quad flat no lead, CSP, chip scale package, and SIP, system in package. These protect the die and enable external connectivity. The full process flow encompasses 8 stages, from wafer preparation to final packaging. Across the industry, average manufacturing yield reaches 87%, with over 1,000 process steps. On the global scale, more than 30 million wafers are produced annually in a $574 billion market. With today's advanced technology, node sizes reach as small as 3 nanometers, packing over 100 billion transistors per chip, all within a 60 to 90-day cycle. Key equipment suppliers include Teradyne, ASE Group, and Amkor Technology. Semiconductor manufacturing, a complex, precision journey. Semiconductor manufacturing is one of the most intricate and demanding industrial processes on Earth. It involves over 1,000 individual steps that collectively transform ultra-pure silicon into the foundation of modern electronics. From raw wafer to finished chip, the journey spans roughly 3 months. During this time, the materials used must maintain a purity level of 99.9% or higher to ensure optimal electrical performance and reliability. The precision of each step operates at the nanometer scale, 1/1000th of a meter, demanding state-of-the-art equipment and cleanroom environments. The result of this ultra-precise process is a chip capable of housing billions of transistors. These tiny switches are what power today's computers, smartphones, and countless other digital devices. The scale, purity, and accuracy involved in this process are unmatched, reflecting the pinnacle of modern engineering and scientific achievement.